learn more about earning college credits with study hall courses, visit gostudyhall.com or click on the link in the description. Early on in our programming journeys, it's easy to think of computer programs as straightforward, tidy paths that start with some input data, like how many frozen lasagnas you eat in a month, and end with an output, say how much money you spent on frozen lasagnas. But programs don't always go straight from A to B. Instead, there's a clever trick that can save us time and effort, getting parts of a computer program to loop back on themselves and repeat instructions. This process is called recursion, and it's sort of like turning your code into a Russian nesting doll that contains smaller and smaller copies of itself. I'm Sabrina Cruz, and this is Study Hall, Code and Programming for Beginners. Recursion, in computer programming or otherwise, it's when something incorporates copies of itself. And the best way to get a feel for recursion is by seeing it in action. In math, logic, art, wordplay, and even in the world around us. You just gotta know where to look. For instance, let's look at the way files are stored on a computer. There are directories or folders that contain files. But a folder can also contain other folders, which can contain even more folders, and so on. It's folders all the way down. So if you want to list every file inside one parent folder on your computer, you'd have to start by looking for files in the first folder. Then you look through every folder inside of the first folder, then every folder inside of those folders, until you've looked inside all of the folders and listed the files lurking in each one. If you mapped out your journey through folders within folders, it would look sort of like branches splitting off of a tree trunk. There are big branches that stick off the trunk, with smaller and smaller branches that split off down to twigs and finally leaves. And just like with the folders, if you wanted to count all of the leaves on a tree, you'd need to check every single branch down to the tiny ends. The key piece of what's going on here, whether you're dealing with computer folders or trees or fractals or Russian nesting dolls, is that the smaller parts resemble the bigger whole. So if we keep zooming in, we're repeating the same thing over and over. At a glance, the idea of recursion might seem more confusing than helpful. While it's fairly easy to picture branches on a tree, it's a little mind-bending to think about a Java operation calling on a copy of itself. But I promise, recursion is a powerful tool that can help us write computer programs more effectively. We can start to wrap our heads around recursion in programming by breaking down the step-by-step process of how a piece of code executes. Specifically, let's revisit one of the main building blocks of Java programs, our old friend, the method. Methods are pieces of code that we define to do some action on placeholder input variables called parameters. Like, we can use a method to multiply any three numbers, or we can use a method that prints "the name's Cruz, Sabrina Cruz," to the screen when we give it any first and last name as strings. Whenever we need to multiply three numbers, or imitate the world's least secretive spy, we can just call one of these methods with different specific inputs or arguments. That allows us to reuse code we already wrote over and over for slightly different situations. As handy as methods are, constantly reusing them can be a little clunky in our code. To go back to that initial metaphor, if we want to picture every task we want to perform as a Russian doll, then repeating method calls is like laying out a huge line of identical dolls one by one in a row. The alternative to that is nesting our Russian dolls. So if you look inside one doll, you'll see an identical doll inside, and so on, forever. Of course, stacking an infinite number of dolls inside each other isn't physically possible, but it's a metaphor. And we're in the programming world now. Like Link's little pouch, we got basically infinite space to play with. By nesting these copies of code inside one another, we can more easily get as many copies of whatever thing we want while keeping everything more organized. This is why recursion will come in handy. Anyway, I could speak in metaphors about recursion, well, forever. But this is a programming course, so let's dive into some real examples. Let's say we want to write a piece of code to write out the same string over and over again. Admittedly, it's not super helpful to have a program give you the same output a bunch of times, but similar code could help someone, say, write out a lot of packaging labels with the same return address. One way to print an address 10 times would be to use the much-loved print line method, which comes built in with Java's system tools, to repeat the same string 10 times in our code, and presto, we get our string printed 10 times to the terminal. Technically, this code solves our problem, but it could be a headache in the long run. For starters, if we want to know how many times the label will be printed, it's not obvious at a glance that the answer is 10. We would have to count out all of the lines. And if we want to change our code to print the label 7 times, or 40 times, or 1,000 times, counting each line of code would get pretty tedious. Instead, we can use recursion to make a computer handle the repetition for us by having the method call on itself. First up, let's create a method called printAddress, whose only job is to print out the address we're interested in. Our program will call this method when it's time to print the address. So, as expected, when we run this code, the method call to printAddress gets the address printed to the terminal just once. But now with a simple change, we could make our method recursive. Inside the definition for printAddress, we can add the method call to printAddress. This is us stacking our metaphorical dolls. And now if we run this code, the address is printed to the screen over and over and over and over, basically forever, until you run out of time, or computer memory, or patience, or all of the above. The reasoning behind this is, when the method is first called, it executes the instructions in the order they're written. So first it executes the printing instruction, and next the method calls itself, which means it runs the whole method again, printing the address and then calling itself again to infinity and beyond. Practically speaking, there's not much use for computer code that does something an infinite number of times, so we need the program to make the decision to stop once the method has been called however many times we want. The good news is that we have a tool for getting computers to make a decision based on some condition, an if statement. We can tame recursion by creating a condition that reflects the number of times a method has already been called. For instance, we could create a new integer variable that acts like a countdown clock for our method. Every time the method executes, we can subtract 1 off the variable, and then we can wrap our method call inside an if statement that only executes if the variable is greater than 0. To see how this plan comes together in Java, let's modify the code we just wrote. First, we'll introduce an integer parameter to our printAddress function named howManyTimes. This will represent the number of times we want our method to run. Next, we'll add an if statement at the very start of our code with the condition that the value of how many times has to be greater than 0. Basically, this says if our counter is done, don't run this method again. Finally, to make our counter tick down, we'll tell the program to subtract 1 from how many times when we call the printAddress method. So now we can call our printAddress method with an argument of, say, 5, and sure enough, our address is printed to the screen exactly 5 times. If we want to peer under the hood to see exactly what's going on here, we can add another print line statement in our code that prints the value of how many times inside the method and run our code again. The first time, the variable is printed as 5. When the method calls itself the next time around, we've subtracted 1 so that how many times is now 4. The following time we get a 3, and so on until the value of how many times hits 0. Except we don't see the variable printed as 0. That's because when how many times finally reaches 0, our if statement stops all the code inside the method from executing. Our recursion is tamed and we have escaped the infinite loop. What emerges is an incredibly powerful tool, the ability to run a piece of code over and over again for exactly as many times as we want. Going back to our dolls, it's like we can control exactly how many dolls fit inside each other until there's one final tiny doll with nothing else inside it. That marks the endpoint and fixes the total number of nested dolls. This also means that they're physically possible again. Lots of the problems we use programming to solve will involve doing some task over and over, like converting all the measurements on a bunch of classic recipes, or converting all the video files from your phone into a format you can watch on your computer. Those aren't super exciting examples, but a huge benefit of recursion is it saves us from tons of mind-numbing work. That's really the magic of recursion, being able to perform the same task exactly 15 or 15,000 times, all by nesting a copy of a task, like one particular instruction that prints an address, that resembles the entire task itself. Dolls within dolls, or branches on branches, which also helps us keep our code a lot shorter and more efficient. With recursion in our programming toolkit, we have new ways of thinking about what we can do with a computer, and we'll continue to build on this idea of repetition in episodes to come. Because early on in our programming journeys, it's easy to think of computer programs as straightforward, tidy paths that start with some input data, like how many frozen lasagnas you eat in a month, and end with an output, say how much you spend on frozen lasagnas. But programs don't always go straight from A to B. Instead, Wait a second. Haven't we been here already? If you're enjoying Study Hall Code and Programming for Beginners and are interested in taking an online course and earning college credit, check out gostudyhall.com or click on the button to learn more. Thanks for watching, and see you next time.